other hand, now let's talk about buffer. Buffer is a solution that resists changes in pH when acid or base is added to it. It is commonly used in biological, chemical, and industrial processes to maintain a stable pH. Buffer is basically a combination of weak acid with its conjugate base or weak base with its conjugate acid. For example, let's take acetic acid as a weak acid and its base is sodium acetate, and a mixture of the both solution would be the buffer solution. Buffer maintain the pH of a solution by equilibrium reactions. And what do I mean by that is when an acid is added to a solution, the buffer that is in the solution that contains the conjugate base would react with the acid that is getting added and neutralize it. And it works the same when base is added. When a base is added, the weak acid would act with the base and neutralize it.
Moving on, we will learn about pH of a buffer solution. For example, we will mix 75 ml of 0.2 molar ammonia with 25 ml of 0.15 molar ammonium chloride. What will the pH be? The question asks us to find the pH. The first thing we need to do is find the mole for each component. How to find the mole? We just need to multiply the molarity with the volume. The volume needs to be in liter. However, the question given us the volume in milliliter. However, there's not be a problem. We just need to convert it to liter. How to convert milliliter to liter? Just divide with 1000. After we get the volume in liter, we just need to multiply with each molarity and we'll get mole for each component. For example, for ammonia, the mole will be 0.015 mole. For ammonium chloride, the mole would be 0.00375 mole. We already find the mole. The next thing we need to do is find the molarity. How to find the molarity? Just divide the mole that we calculate just now with the volume. The volume needs to be the total volume and not just the volume for each component. To find the total volume for this question, just add the 75 ml with 25. However, need to remember that it is need to be in liter. So, divide it with 1000. When calculate, this will give us the value of 0.100 liter. We already have the mole, we already have the total volume. So, we need to find the molarity for each component. For ammonia, we need to divide 0.015 with 0.100 liter. When calculate, this will give us a value of 0.15 molar of ammonia. For ammonium chloride, 0.00375 mole divide with 0.100 liter. When calculate, this will give us a value of 0.0375 molar ammonium chloride.
The molarity for NH3 and the molarity for NH4Cl, we can use it to create the ice table, which is we can get the ice table for the dissociations of our base in water, which NH3 plus H2O will dissociate to NH4 plus 2OH minus. Then we can use the molarity for NH3 that we found earlier in the calculations, and also 0.0375 m for NH4 plus. For change, negative X for NH3 because reactant is being consumed, and plus X for product because products is being produced. And then for the base dissociation constant is already given. It was 1.8 times 10 power negative 5, and then we can use the dissociation expressions to make a KB equation, which is NH4 plus OH minus over NH3. NH4 plus is the conjugate acid for NH3. And then we can insert the formula, we can insert the equations, the value for NH3 with 0.15 minus x and 0.075 plus x into the equations. Then we know that NH3 is a weak base, so it dissociates, it ionizes partially in water. So this will result in small x. That means that we can ignore x because value for x is small. So we can just ignore this one. You can just ignore x, and then we just put 0.0375 times x over 0.15. Then we just use your calculator, and then we found that the concentration of OH minus or X is 7.2 times 10 power of negative 5 mole. Then from the concentration of OH minus, we can find the concentration of H3O plus. We can use the KW expressions, which is KW equal to concentration of H3O plus times concentration of OH minus, and then our KW value is 1.0 times 10 power negative 14, and then this is our unknown because we want to find the concentration of H3O plus, and then our OH minus is 7.2 times 10 power negative 5, and then our concentration of H3O plus is 1.4 times 10 power of 10. So from this value of concentration of H3O plus, we can find the value of pH, which is negative log H3O plus. So just use your calculator. Negative log 1.4 times 10 power of 10 times 10 power of 10. And then our pH is 9.9, so which is we consider as basic.
As for the question in this part, what is the pH if 0.02 mole of HCl are added to a 1 liter of solution made from equal volumes of 0.1 molar acetic acid and 0.1 molar sodium acetate? So we are given the initial pH, which is 4.76. Here is the equation of the dissociation from this question. So in this question, we also use the ice table. So we note that C2H3O2 is the acid, which is reactant, while H plus and C2H3O2 negative, which are products. So here, as mentioned in the question, the HCl is added to the acetic acid. So for the initial for the acid, which is 0.1 molar, and also for the conjugate base, which is C2H3O2 negative, because the ratio mole of this reactant and product in the dissociation equation is the same. As for the change for buffer action here, the reason why acid is plus 0.02 while conjugate base is minus 0.02 is because we are added the acid to the initial just now. So for the concentration of HCl that we are added, we can calculate it from the mole given here with the volume of the solution here. So we divide the 0.02 mole with 1 liter solution to get the 0.02 molar. So that is why here we plus 0.02, And as for conjugate base, we minus it. It is because the conjugate base will be less as for the acid is increasing. And after that, for change, like usual, the reactant, because it been consumed, it will be less, and as for products, it will be increased, so it is plus x. So for the equilibrium, we just plus the 0.1 for the initial with the 0.02 for the added of the HCl just now, so we got 0.12 minus x. And as for conjugate base, we just minus the 0.1 with 0.02, so we got 0.08 plus x. So for the next step, we are given here the value of Ka. So for Ka, we know that the product will be divided by reactant. So in this Ka, we want to know the value concentration of the change here, the x. So we just insert the value from the equilibrium just now into this equation. But in this case, we can ignore this x because the x value here is small, which is equal to the 1.75 times to the time -5, which is the Ka value here. So like in this calculation that I've been wrote, we just times this Ka value with 0.12 and divide it with 0.08 here, so we got the x value. After that, as for the question is to find the pH of this mixture. So we just use the formula of negative log times with the value of this change just now, which is x. So finally we got the answer of 4.58 pH. As if that is all from me. Thank you.
We will figure about how to prepare a buffer of a specific or to find the pH of a buffer with non-concentration. So, how to find the pH of a buffer with non-concentration? We will use Henderson-Hasselbalch equation, which is pH equals to pKa plus log concentration of basic form divided with concentration of acidic form. So, for the second equation is we want to find the pKa. The equation will be pKa equals to negative log Ka. Next, Na is dissociated becomes Na plus and also it will form A minus. So according to this dissociation equation, Na is acid, dissociate, become hydrogen ion and also conjugate base. So how to convert this equation to become pH as a subject? So Ka, as we know, product over reactant. Then we are going to rearrange this equation where the concentration of hydrogen ion will become the subject, where concentration of hydrogen ion equals to Ka times with the concentration of Xe divided with the concentration of conjugate base. Next, since we are going to put pH as a subject, first we need to put log at the both sides for the whole equation, which is negative log concentration of hydrogen ion equals to negative log Ka negative log of concentration of acid divided with concentration of conjugate base. Then, since this is the acid and this one will be conjugate base, we need to turn this become form of the product over reactant. So the equation will be rearranged like this. Negative log concentration of hydrogen ion equals to negative log Ka plus log concentration of the conjugate base, which is the product, and it will divide with the concentration of acid, indicate to the reactant. Since the negative log is representing the P, so we will convert the negative log become P. pH equals to pKa plus log the concentration of conjugate base divided with the concentration of acid. So for this whole equation, it will form as the follows, which is the pH equals to pKa plus log concentration of conjugate base divided with the concentration of acid. So for the next equation will be, we want to find the value of pKa, which is the equals to negative log Ka. So next, as if we want to find the pH, we will use the equation of pH equals to pKa plus log concentration of conjugate base divided with the concentration of acid. So the given pKa is 4.76 plus log the concentration of conjugate base divided with the concentration of acid, which is 0.12. Then we will get the final answer, which is the 4.58.
Based on this question, we want to find the pH of our buffer solution. So first thing first, we have to calculate the concentration of our acid and also concentration of our base. So this is the concentration of our acid. We just simply divide our moles with our total volume. The total volume is 0.140 liter, and this is what we get, which is 0.0428 molar. Similar thing with base. When to find the concentration of base, just divide the moles of the base with the total volume in liter. So this what we get. Second thing, since we want to find the buffer solution, we have to use the Anderson-Hasselbalch equation. This is the formula. Conjugate base divided by acid. So for pKa, since in the question we are given the Ka, so to find Ka, we need to negative log the Ka value. So negative log 6.7 times 10 to the negative 4, you will get 3.17. So just plug in this pKa value, to this equation. So our pH, just use the information that we find from a earlier step and then plug in the equation. So you will get this answer. So your answer, which is the pH, is 3.47. Moving to next question. This is similar. We want to find the buffer. We want to find the pH of the buffer solution. So in this question, we are given Kb. Okay. For the first question, we are given Ka. So how to find Ka? As we know, Ka times Kb is equal to 1 times negative power of negative 14. So to find Ka, we just divide this one with our Kb value. So simply say, we just get this one. Okay, this is our Ka value. So how to find pKa? Similar to first question, just negative log the Ka value, and this is our answer, 9.25, the pKa. Next, we have to find the concentration of acid and concentration of our base, okay, based on the question given. Okay, just a simple step, and this is similar to the first question, times a divide with the total volume. So you will get this is the concentration of acid, which is 0.15 molar, and for our base the concentration is 0.04 molar. Similar to the first question, we just plug in all the information that we have calculated inside this Henderson-Hasselbalch equation. Okay, so after you plug in all the equation, use our calculator, and this is our answer, 8.94. So based on the equation means that we have more base compared to acid, so that's why our pH value here is more than 7 means it in alkali is more to base. So since it is logarithmic 10:1 ratio means a change of 1 pH unit.
Okay, next we need to prepare a waffle solution of the desired pH. From this question, it's asking us to find a mass of sodium acetate that dissolves in 0.3 liter of 0.25 concentration of acetic acid that produce a solution with pH 5.09. Then we need to assume that the solution volume is constant at 0.3 liter. First, we need to do the equilibrium expression, which is we get this. This is the acetic acid plus with water, the reversible arrow, we get acetyl ion plus hydronium ion. So this is the dissociation equation of acetic acid. First we need to do is to determine which one is the weak acid. So acetic acid is the weak acid because it partially ionized with water. And we know that it also donate H+, which will get acetyl ion plus with hydronium ion. Acyl S, if there is with acid, there will be a conjugate base. Acyl ion is the conjugate base. Second, we do the Henderson-Hasselbalch equation. This is the formula, Henderson-Hasselbalch equation formula. And then from this formula, we need to find Ka. Ka as the main subject we need to find here. How this formula become like this? So from this equation, this is the weak acid, this is the conjugate base. This is the formula, right? We know that pH equal to negative log H plus, pKa equal to negative log Ka, plus log conjugate base over weak acid. We rearrange it, log A go to the front, log H plus go to the back. And then from the log rule, we know that if it plus here, we need to multiply it, which we will get log H plus multiply with conjugate base over weak acid. And then we can cut the log here. This is the finalized equation, which is Ka equal to H plus conjugate base over weak acid. Same goes like this. This is the Ka equal to hydronium ion. This is the conjugate base over weak acid. Ka value, this is the 1.8 times 10 to the power of negative 5. And then we continue here. We find the hydronium ion concentration using the pH formula, pH equal to negative log hydronium ion, which we rearrange it, and then we get 8.1 times 10 to the power of negative 6. This is given in the question. The acetic acid value concentration 0.25 acetic acid concentration. And then we solve the acetyl ion. We find the concentration. We rearrange it from here. This equation will be like this. We plug in the numbers we get earlier. This is the acetic acid concentration, and this is the hydronium ion concentration. We get 0.56 concentration. And then we use this stereochemistry. We can cut this. This is given in this question, 0.56. This is the molarity, which is we know mole over liter. We need to find the sodium acetate. So 1 mole sodium acetate, 1 mole acetyl ion times 82. 82 is the atomic mass of the sodium acetate. 1 mole of sodium acetate we cut, and then finally we get the mass of sodium acetate, which is 14 gram.
Next practice exercise. You dissolve 2 gram of benzoic acid and 2 gram of sodium benzoate in enough water to make 1 liter of solution. Calculate the pH of the solution given the Ka is 6.3 times 10 power negative 5. So this question is straightforward. We will use this equation, but we are missing the value of pKa and the concentration of base and acid. So first we will find number of mole. We just use mass over molar mass and we will get the mole. And to find the concentration, we will use moles over volume. We will get the same value with mole because the volume is 1 liter. And then to find pKa, we will use this equation and we just substitute the value into the equation, and then we will get 4.20. And lastly, just substitute everything that we got earlier and then calculate it. We will get the value is 4.13.